For more than a century, a public transport system that keeps pace with Australia's largest capital city has remained incomplete. Now work is underway to fill this gap.
It's the longest transport tunnelling project in Australia's history. At 15 kilometres long and 2 stories high, it'll connect Sydney's northwest suburbs to the city by rail for the very first time. It's called the Northwest Rail Link, and we're going deeper.
This will be a privately operated metro, and in Sydney there's controversy about how it will work with the public system. But for the people building the tunnel, this is an engineering challenge on a massive scale, and it doesn't come much bigger than the tunnel boring machine.
The tunnel boring machine technology is something that's evolved over the last 30, 40 years around the world, but the machines get better and better with every year that goes by, and we're getting some of the best modern machines for this site.
It's 7 metres tall, 120 metres long, weighs in at 900 tonnes. This giant mechanical earthworm can chew through its own body length worth of rock in just 1 week.
And not just one, but 4 of them.
It's a first for Australia to have 4 tunnel boring machines on the same project.
Working 24 hours a day from either end, these monster miners will excavate 2 tunnels, each 15 kilometres long, snaking under Sydney's sprawling suburbs. Taking around 2.5 years to complete, this is the start of a new rapid transit railway that will add to, but run separately from, the existing network. It's Rod Staples' job to navigate the challenges of building a railway in a densely populated, hilly area.
We have quite undulating tunnels that go very deep, and then as they come to stations, they go very shallow, and then they go back down again. So we have grades of between 3% and 4% on this line, which is reasonably steep for a railway, but well within the capacity of a rapid transit type of technology to be able to climb.
Nearly 200 test holes have been drilled up to 75 metres deep. They reveal that the tunnelling route is almost entirely made up of 2 kinds of rock, sandstone and shale.
It's really like carving through Swiss cheese. You cut it, it's very stable, it stands up, it gives you time to put in a permanent concrete lining to support and keeps all the rock in place.
He's been hearing concerns from residents about vibration.
For a lot of people, they may never even know the machine passed underneath them, particularly in the deeper locations, but it is about making sure they're aware that it's coming.
The long journey to design and build the machines started here. Le Creusot is a small city in France with a long and proud history of industry, the kind of town with an old steam hammer as a monument. Here the French design team pieced together the 4 custom-made tunnel boring machines after a competitive tender process based on specifications from Australia.
So we put a very clear specification about wanting these tunnels built so that they're quite dry, so that we don't have water coming into the tunnel.
Built from components made in Germany, France and the US, they're shipped to China, where the machines are put together and tested before being pulled apart and brought to Australia. The multicultural machines are reassembled on site here at Bella Vista. The first, called Elizabeth, has been launched. Another, called Florence, is being built. Engineer Tim Burns is responsible for getting each TBM to do its job underground.
It's like a big caterpillar, essentially. It's got a cutting head and a shield at the front. That's where all the hard work gets done. That's where the excavation happens. And behind that, we've got what we call a backup, which is just a series of trailers, about 120 metres long. And those trailers carry all the essential services and equipment that we need to keep the machine going forward.
What gives the TBM its caterpillar action is its double shield design. The gripper shoes, the machine's hydraulic feet, press against the inside of the tunnel to secure it in place. Then the cutter head advances forward. With its 40 spinning cutter discs, it grinds the rock face into pebbles. From the belly of the TBM, the concrete segments that stabilise the tunnel are lifted into place before the entire tail slides forward, beginning the cycle again.
We've got a very repetitive process. We've got 8,000 metres with each machine to dig. We dig it in 1.7 metre cycles. So we need to try and optimise all of the little operations on the critical path in each cycle to make sure that we can get to the end as safely and as fast as possible.
It will take 98,000 of these concrete segments to build the protective lining of the two tunnels. All are manufactured next to the tunnelling site. Jeremy Glasgow is a civil engineer running his first factory.
It's like any major operation. It's not just about the operation itself, it's also about the supply chain. And basically the TBM is not going to go anywhere without the supply of the precast segments. I guess what's unique about this project is that we've got 4 TBMs. So the consumption rate in terms of the amount of segments and rings that the TBMs use is very high.
To meet that demand, the precast facility runs around the clock. It mixes, casts and kilns hundreds of segments a day to a strict recipe that combines high tensile steel wires and polyfibre with cement. And one other key ingredient.
Ultimately, when it comes down to batching a high-performance mix, there's one critical component, which is moisture control. It's all about controlling the water.
While a precise ratio of water to cement is essential for strong segments, there's another design innovation that keeps them waterproof once assembled. A rubber gasket that's built into the concrete.
What it should mean is a drier tunnel. Having a casting gasket will give us a really good chance of having no leaks and a really watertight tunnel. The design life of the tunnel is 100 years, but in my opinion, it'll last for a hell of a lot longer than that.
Each segment is checked for flaws and barcoded. Small changes repeated thousands of times can have a major impact overall.
It's about constantly working on improving the process, and there's always constant improvements we can make.
But attention to detail doesn't end there. Safety is paramount. At the front lines of the operation are the men and women to work on board the 4 TBMs.
It may look like we're underground, but this replica tunnel is as close as you get to the real thing above ground. Every member of the 15-person crew has to undergo a week's intensive training before they're qualified to run the tunnel boring machine.
Tunnelling is a specialised sector of the construction industry. It's a lot more riskier than construction and building work.
Terry Sleeman is the project director. Things have changed since tunnels were built by workers at the rockface.
It's all about safety. Back in the Snowy Mountain days, the injury rate, and it's common knowledge amongst tunnellers, was basically a man a mile. Totally unacceptable today. You know, we look at the horizon and there is a wealth of work in terms of major projects. So it's almost a business imperative to train the next generation of tunnellers.
One of the really impressive features of this tunnel boring technology is that I can experience the whole thing in virtual reality before I even go underground in it. Top of the tunnel's just around here, and if I look over the edge of the railing, and I do get a sense of vertigo, and I'm looking down at all the segments that are below me that are going to be wrapped around the side of the tunnel. So having been here, well, there you are. I'm feeling more than prepared.
Now it's my chance to head underground for real and get on board Elizabeth, or TBM1.
We're excavating right at the moment, cutting through this Ashfield shale. So you can see the materials coming out of the cutting head on the machine conveyor 1, then out onto the tunnel belt for removal to the facility on the surface.
So how fast is the machine moving forward at the moment?
Penetration rate at the moment will be about 60 to 70 millimetres per minute.
Right. But is it the kind of rock pile you like to see on your conveyor belt?
Yeah, this is a great view. Belt full of dirt is just fantastic. It's all happening.
All right, this guy wants to do some real work. Sorry, mate.
Being underground here is claustrophobic, hot and noisy. It's like being in a full-sized factory that's been crammed inside a small submarine and buried in the earth. Keeping this juggernaut on track is crucial, but how do they know where it's heading?
This is where the guidance of the TBM happens. So what we've got right here in front of us is a theodolite with a laser attached on a series of known benchmarks on the surface. You can see this laser beam shining forward to a video target, which is right at the front of the TBM. So that's in a known position, shining onto a video target that's in a known position, therefore the front of the TBM is always in a known position.
You don't get straight into the laser beam.
You certainly don't.
There's only a 50mm tolerance in any direction before the TBM starts to drift off course. So drivers like Jed Guttridge constantly monitor the data coming from the laser guidance system and steer Elizabeth with hydraulic rams.
Yeah, it's running pretty good. We've been getting pretty good meters at the moment.
What's you like to drive?
This machine's really good to drive. It goes really fast.
When you say really fast, what's top speed?
We can get up towards 100mm a minute, which is like pretty fast for a TBM.
At the moment, it's taking about an hour to grind the 1.7 metres of space needed to install another 6 segments that make up one ring of tunnel lining.
The segments have a pattern that they have to go together in, and we've got some help of a computer-guided system to give us the optimum arrangement of segments. And yeah, one big jigsaw, and it all goes together as we advance.
And each segment has to be sent down from the surface in exactly the right order, or the whole process grinds to a halt. Once a complete support ring has been assembled, there's one last job. To fill in the space between the bare rock and the concrete ring, a multi-part grout made from cement and bentonite is mixed with a setting agent, sodium silicate. When it's pumped into the tunnel, the grout has to set in under 15 seconds to lock the concrete segments into place for the next 100 years. Pipes deliver the vital fluids into the TBM, and the conveyor belt brings out the crushed rock. In the end, a total of 2.8 million tonnes will come from the tunnel excavations.
2.8 million tonnes of rock may not mean very much, but try equating that to 1,000 Olympic swimming pools of material coming out of the ground.
The aim is to reuse the spoil as solid fill or for making bricks. But the biggest recyclable of all is Elizabeth and the other 3 tunnel boring machines. Elsewhere, the end of a TBM's job is also the end of its life. It's lowered into an underground tomb and buried in a thick layer of concrete. Despite being worth millions of dollars, their retrieval is so expensive that it just doesn't make financial sense to rescue the machines. However, in the case of Elizabeth and her 3 sisters, at the end of their journeys, they'll see the surface once more, and another role in the nation's ever-evolving transport network.
That's what we're here for. We're here to leave a tunnel for future generations.